off talking about that tea kettle, and it's just a handle. We're going to go through this pretty fast. We're not going to spend a lot of time on the scientific method because, frankly, you've probably had it every year since 7th grade, I'm hoping. But I want to talk about how to distinguish what's science and what's not science. And so this CONPIT is a nice acronym. The C is consistency. When we say that an explanation is science, it's got to be consistent with the way that other things that we are familiar with in science and in the universe work. So if you say, well, you know what, the laws of gravity work in the same way, in the same scale, everywhere in the universe, except right here where actually some other thing is going on, that's inconsistent with what we know. When we have a scientific explanation, it has to jive, essentially, with all the other stuff we know. And one of the big things about science is that we pretty much assume that natural laws work the same way everywhere for all time. So gravity has always worked. There was not a magical point when gravity kicked in. Like, okay, gravity's now in effect. We can look at the formation of our solar system, and it's all down to gravitational attraction. We can look at the behavior of molecules, and it's down to forces of attraction and repulsion between them. So, you know, those things are consistent throughout time, throughout history, throughout the universe. And if we have an explanation, it has to be too. And the other big thing, so this is consistent, and you have this in your notes, consistent. It also has to be observable. Okay? So if we're going to talk about something as a scientific explanation, we have to either be able to collect information about it with our senses, the actual event, the actual function or material, or evidence of it. So in chemistry, there are a lot of things that we can't observe directly. We cannot observe the interactions of subatomic particles directly. We can't observe the interactions of molecules directly. We can't look at a molecule under a microscope. But we can look at evidence of how things behave. And that evidence has to be observable with our senses. And so, especially when we get into the history of the atom, we'll talk a lot about how specific things are observable evidence of the behavior of tiny things that you can't directly observe. Okay, and it's got to be natural. So our explanations have to be natural. We can't invoke the supernatural in science. And so the supernatural is everything from elves to God. Those are all things that are beyond the realm of the natural. It doesn't mean that we can't think about them, but they're not something that we can explain things with in science. Okay? So those are things that are beyond the realm of the natural, and it's just a different domain of thinking. You know, just like we talked about the tea kettle. In science, we can explain why it's whistling in physical, natural, observable terms. We can't determine who turned it on. So that natural means we don't have any information about that. And so we just kind of can't go there. We can't invoke a supernatural explanation. Predictability. So I will pause for a moment. So science allows us to make predictions. Science is just a tool, and it's one tool of many for thinking about the world and the universe and the history of everything. But the big thing about science is it allows us to predict. So especially like when we do the history of the atom, the development of atomic theory, you're going to look at a lot of scientists who said, well, I believe this, and if that's the case, then this should happen when this happens. Well, then you make this happen. Does this happen or not? So you're using that tool of prediction and, you know, confirming or denying hypotheses. Science allows us to make predictions, and that's really powerful. Science is also testable. So again, when we get into the atomic theory stuff, every single thing that was ever proposed by the people who worked on building the model of the atom we have now, at some point they tested. They took the hypothesis that they had created and they found ways to test it. And it's tough because in chemistry especially, in biology, we can go out and count critters. We can count bacteria. We can count deer. We can count fish. We can measure a lot of things directly. In chemistry, it's not that easy. Because a lot of the things, especially when we're talking about atomic theory, a lot of those things are not directly observable. So you have to find proxies for them, or you have to look at the behavior of, groups of matter and make inferences about how the atoms that make up that matter are behaving. That's tough. That's not easy stuff. But it's been done really well and tested. And science is tentative. This is the last one for the con pit. Tentative means it's subject to change. When I started teaching chemistry, I used to say, nobody's ever taken a picture of an atom. Can't say that anymore. And I'll have to find the image, but means were developed to actually image an individual atom. Now, it's not like your school picture. It's a fuzzy, multicolored blob, but it's an image of an individual atom. We know things about atomic structure that we didn't know 100 years ago. Science changes all the time. And whatever, when I say science is not a body of facts, it's a way of understanding the world. Whatever facts you are learning, because you are going to learn a body of facts. I mean, it's the basic, it's like learning your ABCs. You're learning the alphabet of science in those facts. Using them as the next step. Whatever facts you're learning today are the best we know at the moment. It is the best information we have. It'll change, guarantee you. Some of you are heading into careers in science, like I said, higher than usual percentages in chemistry and physics of students who are heading into something to do with science, whether it's medical or engineering or biology or whatever. In your lifetimes and in your careers, you will see things shift, which is fabulous. It's exciting. In science, we don't get bummed out about things changing. It's like, wow, cool, hey! It's a wonderful thing. So it does change, and that's what we expect. Okay, so, scientific method, we're not really going to do. What I am going to say is, I would put an S on that, because I'm really, frankly, sort of offended by the cookbook, cookie cutter. First you do this, and then you do this, and then you do this. Because it's not like that. It's chaotic and multi-pronged, and there are things going on lots of fronts all at once, all the time. And the big scientific tools are observation and questioning and collecting information, collecting data. Those three things are things that you do in everyday life, and you should. Being really observant, noticing things about you, not leaping to conclusions based on what you notice, but just collecting data. That mental cataloging that you all do every day. Teenagers do a lot of mental cataloging about one another and themselves, I notice. And I was a teenager once, many, many, many years ago when dinosaurs walked the earth. You're running a mental catalog of lots of data. Run that catalog about the whole world. It's a powerful tool. You've got a powerful tool. Forming hypotheses. Hypotheses, this is my other pet peeve. A few of you have heard this before. It's not an educated guess. Good Lord, please don't say that. It's a working explanation. A hypothesis is an explanation for things that you've observed. But it's not a guess of any sort. It's a working explanation. It's subject to change. You might find out that your hypothesis is totally wrong. One of my favorite quotes from one of my favorite living scientists, David Green is a physicist, and he's been working on string theory for the last 20 years. He's a physicist, I think, at Columbia. And I got to see him speak a number of years ago. He came to YSU and did a talk when his book was published. And he said, I guess at that time he had been working for 20 years, so he's been in the field like 30 years now. He said, yep, every day I go to work and I try to disprove what I've been working on, and I could wake up one morning and we could have found the linchpin thing that shoots string theory straight down the tubes, and then I have to figure out what's next. Wow. So string theory is a hypothesis still at this point. You know, it's called string theory, but I don't know that it's really attained that status. Theory is pretty serious in science. And they're trying to chip away at it. So if you are working on it, what you are doing is trying to break it. You're trying to disprove it. We never prove anything in science. We just disprove stuff. You know, and so scientists tend to say things like, well, thus far, you know, the evidence has been consistent with, which means we haven't broken it yet. You know, thus far we don't have any observations that are inconsistent with. We haven't broken it yet. But it doesn't mean we've proved it true. It's a big difference. And of course, you know, as you test hypotheses, as you get more information, you draw conclusions, and in science, you got to share that stuff. I'll share some websites with you later in the year. But it's a set of tools. Now, that's all we're going to do about scientific theory or scientific method formally. Let's talk about scientific notation. So, show of hands. And you do not have to show them, like, you don't have to do this. You can be really subtle. But 0 to 5, your comfort level with numbers in scientific notation, putting numbers in and out of scientific notation. 0 to 5. Like 5, I'm a rock star. I could do this asleep, upside down, hanging by my toes at 2 in the morning with no coffee. 0, I have never heard of scientific notation before. I have no idea what you're talking about. So where are you at? 0 to 5. 4s? Okay, mostly 4s, some 3s. That's okay. You're going to get better at using it in this class. We do use it a lot. So you understand the basics. If we have a number like 3,246, we can express that, you know, the decimal is here, even though it's not shown. And we can express that as a power of 10 by moving that decimal in essence. 1, 2, 3. So we say it's 3.246 times 10 to the third. This is really critically important when we get into very, very large numbers. So 3,0,0,0,0,0,0,0,0. Let's see. Hey, I got it. Okay. So that number happens to be the speed of light. But we don't write that. We just write 3 times 10 to the 8th meters per second. Because nobody wants to write all those zeros. So this is pretty easy. Putting very tiny numbers, and this is what we use scientific notation for more often in chemistry. So let's mass of an electron. What is that? I'm gonna get this wrong, but it won't matter because nobody else knows it either. 0.0000000000000. There are a lot of zeros. 19 something. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Gives us 1.9 times 10 to the negative 17th. Okay. Easy, and I think you all know how to do it. A couple of points about scientific notation and correct scientific notation. Scientific notation always consists of, this space is one number that is between 1 and 9. Okay? A single digit. If you give me 2 digits there, I mark it wrong. It's bad scientific notation. So it's a single digit between 1 and 9. And then this is as many digits as you need or are allowed, and we'll talk more about the rules for that later. And then it is times 10 to the something. Numbers that are smaller than 1, it's a negative exponent. Numbers that are larger than 1, it's a positive exponent. And you know that. I'm gonna fess up. I'm gonna admit this. Some of you have heard this. Just a few of you. Most of you have not. I cannot reliably tell left from right. I know which way is north, south, east, and west. Left and right I have to think about every time, and while I can certainly do, yeah, this is my right hand, this is my left hand, when we start talking about your right and my left and your left and my right, and oh my God, I just give up. I quit. My brain shuts off. I apologize. So I tend to talk about in front of and behind the decimal, because students will say, well, am I moving it left or right? I try never to answer that question because I am deadly terrified that I will answer it wrong. It will become cemented in your brain, and then it's all my fault when you screw it up. So I avoid left and right. Sorry if you're really attached to them. I just can't do it. So I tend to talk about in a number like 7.26. The 7 is in front of the decimal, and the 26 is behind the decimal. Everybody okay with that? Okay. I don't think it's that uncommon, but I've had a few students who've gone, is it left or right? I don't know. Anyway, the part of just putting them in and out of scientific notation is pretty easy for most students at this level. Most juniors and seniors who I get in chemistry have no problem with that. Here's where it gets hairy. You get an answer, and that answer is 426 times 10 to the second. That's incorrect scientific notation. Don't give me that because I'll mark it. And we'll take away all your points. But you'll lose points for that being bad scientific notation. How do I fix that? Tyler? Well, that's where the decimal needs to go. I know that. But then what is it? Colin? Okay. Now, this one's an easier example. So, yeah, we know that it's actually 10 to the 4th because the decimal needs to go here. What I tend to do, and it's not so critical with a number like this, because this one's actually an easy one to manage, but when you get up into things that are like much larger or much smaller, I actually tend to do this. I go, okay, 10 to the second, so let's fluff this back out. It would actually be there. And then I go 1, 2, 3, 4. This is the thing that students most commonly screw up. And I have developed just habits to stop myself from screwing up because it's the kind of thing that I tend to screw up too unless I build my habits. And so I literally, every single time, I do my what I call my fluffing up, getting it back to the actual number it is on the bottom side, and I do my bringing it back into proper scientific notation on the top side. You can do it some other way. I don't care. It's you and your brain and your homework and your test. But I would suggest that you develop a method because students really commonly screw that up. Because when you get a number, I'll show you the ones that are much harder. 437 times 10 to the negative 9th. Ooh, I hate these. I hate them. These are the ones that people screw up. Because whether you're moving the decimal this way or that way, when it's a negative decimal, am I making that number larger or smaller? So what I tend to do, again, and I very often don't draw out all the zeros I need to, but I will tend to go, okay, this is to the negative 9th, so that really means 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll draw in an imaginary 0 there. Well, then that would be 1, 2, 3, 4, 5, 6. That would be 4.37 times 10 to the negative 7th. maybe you don't make this mistake. Maybe this is not a mistake that you're going to make a lot. But I can say that about 50% of chem students starting out the year doing things with scientific notation a lot will miss about 50% of problems like this. That's based on, I think, 8 years of data of teaching chemistry. So develop a system for yourself, because I'm just telling you, it's a pitfall, and I'd like you to not make it. I didn't used to know that that was a pitfall, and now I do, so now I talk about it. When you add and subtract numbers in scientific notation, if I take, 2.2 times 10 to the second plus 3.4 times 10 to the first, can I add those as is? No. The exponents have to match. So you're moving exponents around, because really, if you look at what those numbers actually are, that's 220, that's 34. So you can't add the 2.2 and the 3.4. What you can do is this. 2.2 times 10 to the second plus, well, I can put that 3.4, I can make that times 10 to the second. So if I do this, now it's 34, this is 0.34 times 10 to the second. Note that that's not correct scientific notation, but it's okay as an intermediate step. Your final answer has to be corrected, but it's fine as an intermediate step. So now I can add my 2.2 and my 0.34, and all I do is I add the front part, and the exponents don't change. The exponents do not change. So this is going to be 2.54, yes, times 10 to the second. And that would be my final answer. We haven't talked about sig figs yet, so. Okay. Good with that? Same thing for subtraction. And you get good at fixing your answer. You get good at moving those decimals. We don't use addition and subtraction as much as we use multiplication and division, so let's focus on that. If I have 7.41 times 10 to the 9th times 9.43 times 10 to the 3rd. These are easy, these are beautiful, these are lovely, and you will use them a lot. Once again, all we have to do is take this front part, perform the operation that we're doing. So we're multiplying those two, so we have 7.41 times, actually I will use that, times 9.43, and the whole thing is times 10 to the 9 plus 3. When we're multiplying, we add those exponents, which you pretty much should have already had from math, but this is sort of a review refresher. So what would be our raw answer there? Raw answer of 69.8763 times 10 to the what? 12. Don't give me that as a final answer. Why not? Yeah, the scientific notation is wrong. So you're going to have to fix that. And I honestly, once I get back in the groove of this every year, I don't have to fluff it all the way out. I just start the process, and then I can go, oh yeah, okay. So that's my little trick. So I'm going to go, okay, so then we're going back one more than we came. So that's going to be to the 13th. So my final answer is 6.98763 times 10 to the 13th. We have not yet learned the rules for rounding. It's not random. This would actually be 6.99. That's how many we could have. But we haven't talked about those yet. So that would be our final answer. So, Qualitative versus quantitative. Have you heard these terms in a science class before? Okay. Tell me what quantitative data is. I'm going to do shirt color lottery. I haven't done this in a long time. Not recording. Quantitative. If you give me a quantitative piece of information about the boiling point of water, you're going to tell me that water boils at 100 degrees Celsius. If you give me qualitative information, you're going to tell me that when water boils, it turns to vapor. Both are scientific pieces of information. Both are something that we would use in chemistry, but one is qualitative, one is quantitative. So measurements that you make in a chem lab represent quantities. And quantities are things like length, volume, mass. This is a real subtle distinction, but it's kind of important. So a quantity that you can measure would be mass, length, time, volume, area. Those are all quantities. Notice that those are not units. Okay? Those are not units. The unit is used to measure the quantity. So what units would we use to measure mass? Kilograms, grams, centigrams. Yeah. What units could we use to measure volume? Cubic centimeters, cubic meters, liters, milliliters. The units and the quantity that they're measuring are different. Okay. We use SI, which stands for System International. It's the International System of Units. It's used by scientists all over the world, which means that they can communicate easily. There is one exception. There's one place in the world where they don't use SI standardly. That'd be us. There was a Mars lander that crashed because engineers did not convert one set of measurements from feet and inches into meters. I'm not kidding. Millions, billions of taxpayer dollars smashed into the surface of Mars because we didn't convert. I gotta find that story again. I saw it years ago. I mean, it happened, but anyway, there was a conversion because we weren't using SI units. So SI units, System International, they're used all over the world, and we can do what we call derived units. So these 4 SI units, which you can't see because the slide isn't here. I forgot about that. Kilograms, which is not what we would typically consider a base unit, but is the SI official unit. Meters, Kelvin, and moles. So these are the SI official units. It's really tempting to want to say that grams are the SI unit for mass, but they're not. It is kilograms. If you would be so kind as to look on, you don't have books? That's right. Go grab a book. On page 34 in your book, you have this chart, and that lists all the SI units. The 4 that I gave you right here are the ones that we typically use in chemistry. And starting out, the ones that we'll use will be the kilograms, the moles, for the most part. We'll do a little bit of stuff with dimensions of length and area, but not a whole lot. We'll stop there. We're going to start conversion. Actually, you know what? So tomorrow when you come in, I'm going to have a scientific notation FIP quiz for you. It's going to be real short, but I want to make sure that you're as good as you think you are, because I'd rather that you discover any shortcomings now than on the test. The measurement quizzes. You should all have a grade for those, a FIP grade. Based on that video, that quiz, and what we've talked about today, do you have questions? Yes, ma'am. General questions on the measurement concepts. Anybody? And this is not like a going once, going twice kind of thing. If a question pops up tomorrow, ask it then. So tomorrow when you walk in, you'll have the scientific notation FIP quiz. It'll be really short. We're going to start doing conversions. It's bizarre because you've done SI conversions before. It tends to trip people up. So we're going to spend a chunk of time working on it together. What I want you to do tonight, this is your homework for tonight, watch the Getting Converted video on the YouTube channel. It's linked from that page. Take the quiz. So when you walk in tomorrow, you'll have your SI quiz, and your Getting Converted video should have a grade for that. That's it. Other questions, comments, concerns, cookies, queens, queries, querulous, comfits? No? Good. See you tomorrow.